Okay, so we're going to start this question by talking about the muscle sensory receptors. So first we'll start with muscle spindles. And these are stretch receptors. So these muscle spindles respond to stretch. So I'll go ahead and draw what one looks like here. We have two different types of fibers in each one of these. In each one of these muscle spindles, we have two different types. In these muscle spindles, we have bag fibers and we have chain fibers. And so go ahead and kind of talk about the difference between these, the chain fibers and the bag fibers. So the bag fibers are type 1A fibers that are responsible for the high stimulus, the actual movement of the stretching of the muscle. And these respond to, they give information about the rate of stretching. Like if you were to extend your arm at the elbow, that process of extending the arm would be activating those bag fibers, those 1A type of fibers, where chain fibers are type 2 fibers, and they are meant to give information about the static muscle. So when the muscle is not moving, that's when those chain fibers are activated. So this gives information regarding the duration of the stretched muscles. So more about these fibers. The bag fibers are innervated by dynamic gamma motor neurons, and these are innervated by static gamma neurons. So that is the muscle spindles, which again are responsible for the stretch within a muscle. So now we will go ahead and talk about the Golgi tendon. And so the Golgi tendon, what I like to think of is it acts as a protection for our tendons. The Golgi tendon is kind of a protection against us using our muscles to rip our tendons off of our bones, which can cause damage and injury. So the Golgi tendon is something that can be used for inhibitory reasons to protect ourselves. So say if we have a leg here that is bent at the knee, and here we have the quadricep muscle and the tendon going down over the knee, and here we have the hamstring. So if we are trying to shorten this quadricep muscle by pushing the leg up, but if we're holding this leg still, then there's going to be resistance. So this quadricep muscle is going to be constricted. It's going to be building up tension, but it won't be shortening because we have something blocking that shortening. So what's going to happen is there's going to be a lot of tension building up here on the tendon. And so before we can get to the point where this tendon will just be pulled off of the bone because of the building tension in the quadricep, the Golgi tendon will be here and it will sense all of this pressure. And so it will send a signal to the spinal cord, which will basically do the opposite of what's happening here. It will inhibit the quadricep from being able to contract here, and it will activate the hamstring so that ultimately we will have movement back away from that wall that was holding us there, so that we won't put too much tension on these tendons here. So I like the Golgi tendon is kind of an inhibitory mechanism for our protection. Okay, so now we're going to go ahead and talk about reflexes. So what I've drawn here we have another example of the leg that is bent, and we'll talk a little about the stretch reflex. So what happens with the stretch reflex, we kind of like to give the example of physicians using the little hammer here that looks like a triangle. And what they do is they will go ahead and hit the patellar tendon. And so what will happen is there will be kind of a little bend in the tendon here, and it will lengthen. So what happens is a sensory neuron will sense the tendon shortening right here and will come to the brain and tell the brain that the tendon is lengthening. The tendon is becoming longer. And so because of that, we will have a innervation of the quadricep muscle that is excitatory, and it will cause the quadricep to flex. It will cause the leg to go up in this direction. And we'll also have an inhibitory nerve sent to the hamstring that will inhibit the contraction of the hamstring and stimulate the contraction of the quadricep. And that is to keep the tendon from lengthening anymore. So now when talking about the withdrawal reflex, I'll go ahead and draw an example here of an arm and a hand that is reaching out to touch maybe a hot surface or something like that, like a stove or something. So what we know happens is when we touch a hot surface, we will have a sensory neuron that will travel to the spinal cord from the hand that will tell the brain that we're feeling pain, telling the brain that there's something hot that we're touching. And so what we're going to do here is if we have the bicep here and the tricep here, this motor neuron will come from the spinal cord and it will be excitatory to the flexors, and it will be inhibitory to the extensors here like this. So we know that after that stimulus happens, we will have the arm, which will now be flexed because of the bicep being activated and the tricep being inhibited. So the arm will want to move away from this stimulus that was causing pain. And so that is the idea behind the withdrawal reflex. Our sensory neurons will travel to the spinal cord and activate alpha motor neurons that will stimulate the flexors and inhibit the extensors, causing the movement of the elbow and movement of the arm away from that stimulus that caused pain. Okay, so now to talk about taste. We know that taste happens because of chemoreceptors. So first what I'll do is I'll draw a cell on a taste bud, and everything that is below this dotted line is going to be the same regardless of the taste. So we know that we have the SR here, and we also will have calcium gated channels here that will ultimately go and release neurotransmitters that will be in this neuron that will go to the brain. So each one of these is the same from this dotted line down. But now we can talk about the different categories of the cells depending on the taste. So first we will talk about salt. And here with the salt, we have a channel that is called the ENaC channel. And obviously that will be what allows sodium to come in to the cell when we taste something salty. when we taste something that is sour, here we have another cell, we will have another ENaC channel, but instead of sodium, we will have hydrogen plus ions going into the cell, and we will also be closing the potassium leak channels. Okay, and then the third type we have is for sweet, bitter, and umami tastes. And these will look like this. Instead of ion channels, here we will have a G protein. And here we will have phospholipase C. And so we know that phospholipase C, we will have IP3 that will make its way down here to the SR. That will influence the signals that are sent to the brain through the neuron. So these are the three different categories of taste cells that we have all along our taste buds, which interact differently based on the specific taste that we have in our mouths. Okay, so now when talking about smell, I'll go ahead and draw a nose here, and above the nose we have what's called the cribriform plate that will separate the top of the nose from the area of the brain. And so we know that the neurons here, we will have different neurons that will come up here into the olfactory bulb. And they will end up sending action potentials and signals back to the brain through that pathway. And so now to talk about how we receive smell and the pathway of the chemicals that the chemicals go through in order to send those action potentials. If we go ahead and draw a dendrite here. On this dendrite, we will show a G protein here, and we will also show, here we have adenylyl cyclase. Adenylyl cyclase will then produce CAMP, and that CAMP production will cause the opening of these channels here, and these channels will allow both sodium and calcium to come into the neuron, which will depolarize it, and there will also be a chloride channel that is opened. That chloride will exit the cell, which will further depolarize the cell and send an action potential up the neuron and to the brain based on the smell. Okay, and so now to wrap up this question, we'll go ahead and talk about how hearing works. So here we have the outer ear, the middle ear, and the inner ear, or the cochlea. So we know that we will hear vibrations. Those sound waves will come and travel from our outer ear through our middle ear and to our inner ear and to our cochlea. So to label right here in red, we have the basilar membrane, which will be a key part in talking about the vibrations that we hear and how we're able to hear sound. So now what we're going to do is I've drawn a picture of a cross-section of the cochlea here, and that is what we've drawn here, and this will kind of be what we use to explain how these vibrations can cause these action potentials that help us to hear things. So here we have the tectorial membrane, which is another key player. We have the perilymph up here, the endolymph, and perilymph down here. And these are just the different regions of the cochlea. And here we have hair cells that are embedded into our tectorial membrane. And so what happens is this tectorial membrane is a softer material that is going to cause this movement to happen when there's a vibration, when we feel those sound waves. Here highlighting in red again is the basilar membrane. And so what happens when this tectorial membrane, when it senses those vibrations through those waves, it's going to move this way along these, pushing these hair cells from the shorter hair cells to the longer appendages of the hair cells. And so go ahead and blow up a hair cell, and we can talk more about what a hair cell does. So what happens when the tectorial membrane will go ahead and push on the hair cell, and that will cause the hair cell to move. It will kind of bend its appendages here due to that movement. And so here we have channels, potassium channels, that are connected in between each one of these appendages of the hair cells. And so when this movement happens, the tectorial membrane moves, what will happen is these channels will open because they will no longer be connected to each other due to that vibration. And so when these channels are open, what we will have is an influx in potassium. And hearing is one of the only mechanisms where potassium is what is going to cause a graded potential, and an action potential will be based on this influx of calcium or potassium. So once we have this potassium that is building up this positive charge here in the hair cells, we will have different channels along the hair cell membrane. And this channel will be a voltage-gated calcium channel, which will open due to this depolarization, and more calcium will flow into the cell, which will cause these vesicles full of this neurotransmitter to depolarize and ultimately exit their neurotransmitter onto a neuron, which is attached to each one of these hair cells. Each one of these hair cells is innervated by a neuron, which will then travel to the brain, telling us the different frequencies that we hear. So